Ionic Radii. Let's look at it in two different ways. For a cation, always have a size that is smaller than the neutral atom because the outer orbit, if you want to think of outer orbit as the valence electron shell, you can. Because the outer orbit has at least one less electron. Because it has one less electron, there is going to be less electron to electron repulsion. All right. Same thing could be said about the anion, but just a different result. Anions always have a size that is greater than the neutral atom. Because the outer orbit has at least one more electron. So this would translate to more electron to electron repulsion. That's all the writing I'm going to do. That's all you need to know. Let me look at a few examples here. All right. If we look at, let's say, oxygen. And let's compare it to, let's say, fluorine. Oxygen proton number of 8, neutron number of 8. We got to draw 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, sorry. There we go. 1, 2, 3, 4, 5, 6, 7, 8. Good. We'll do the same thing for fluorine. Fluorine has 9 protons. It's going to have 10 neutrons. We need to draw 9 electrons. There we go. Oxygen, because it is a group 16 element, it is going to gain 2 electrons. Gain 2 electrons. So it'll gain it here, and it'll gain it here. Fluorine, because it's a group 17, it's going to gain 1 electron. So it's going to be gained over there. Now we have to look at it in terms of which one is going to be larger. The larger one is going to be the oxygen. Why is that the case? How many electrons do we now have? We used to have 8. Now we have 10 electrons. Fluorine used to have 9. Now it has 10 electrons. Do some simple math here. Oxygen used to have 8 protons. Eight is going to be positively charged because protons are positive. Now has 10 electrons. Negative 10 because electrons are negatively charged. You now have a charge of 2 minus. This is why oxygen is a 2 minus charge. All right. Next we have the fluorine. Fluorine used to have 9 protons. It's going to be a positive 9. Then we're going to have the electron number, 10. Sum will be negative 1. So it has a charge of negative 1. The greater the charge, the bigger it's going to be for an anion. Why? Look at the amount of protons here. We have 8 protons, 10 electrons. Fluorine, 9 protons, 10 electrons. They both have the same amount of electrostatic repulsion. 10 electrons of repulsion, 10 electrons of repulsion. Which one is going to be more compact? Squeeze tighter together? The oxygen or the fluorine? It's going to be the fluorine. More compact. Why is that the case? Fluorine, again, 9 protons. There is more protons in the middle. If there are more protons, this means the electrons on the outside are wanting to go towards the center more because there is a greater number of protons. This is what they want. More protons are better for them. Again, they're attracted, right? The negatives attracted to the positives. Same thing here. 10 electrons, same amount. Only 8 protons. It will still be attracted, but not as much. It has 1 less proton than the fluorine. So it's not going to be as fun. This is why fluorine is going to be smaller. If we look at, let's say, lithium, let's say beryllium. Lithium, I'm not going to draw the protons and neutrons on the inside, just for the sake of time. Lithium, 1, 2, 3. 3 electrons. You gotta remember it's positively charged in there. Beryllium, again positively charged as well, always the nucleus. Beryllium has 4 electrons. All right. In order for lithium to be happy, it's going to lose 1 electron because it's a group 1 element. Beryllium is going to lose 2 electrons. Sorry, maybe I'll do 1 electron up here and then maybe 1 electron there. So lost 2 electrons. So lithium used to have 3 protons because lithium has an atomic number of 3. Hence 3 protons, they're the same. Used to have 3 electrons, but it lost it. So now it only has 2 electrons. Positive 3 minus 2. The sum gives us a plus 1. Li has a charge of plus 1. Beryllium, 4 protons. Again, atomic number is 4. Electrons used to have 4. Got rid of 2 of them. Now you have 2 electrons. Positive 4, negative 2 gives you a plus 2. Beryllium has a charge of 2. Which one is going to be greater? in terms of its size, in terms of its ionic radii. Think of it this way. The beryllium, when it loses 2 electrons, there is going to be less electrostatic repulsion. So if we were to look at it this way, get rid of that electron, get rid of that electron. Both have 2 electrons. 2 electrons. This one also has 2 electrons. Lithium, however, still has 3 protons. 3 protons. 3 protons. Okay? Sorry, beryllium has 4 protons. What am I saying? 3 protons in the middle, 2 electrons on the outside. Beryllium has 4 protons in the middle, 2 electrons on the outside. Which one is going to become more compact? It's going to be beryllium. Why? The electrons want to go towards the middle. We've been emphasizing this all the time. 4 protons. This is greater than 3 protons. Electrons are going to be very happy. They want to go closer towards there. The more of them there are, the more fun it's going to have. Lithium. Still, these electrons want to go towards the center. But there's only 3 protons in there. It's not as great as 4. So, beryllium is going to be more compact. More compact. And if it's more compact, it's going to be smaller. So, the greater the positive charge, the smaller it's going to be. Let's look at a few examples. How does the amount of charge in the nucleus of an atom affect the size? We've established the greater the positive charge, the greater the positive charge, the smaller it will be, the ion. Same thing could be said similarly. The greater the negative charge, the greater it will be, the bigger. That's how we answer number 15. Let's put this into a question. That's the best way to check our comprehension for understanding. All right. Let's do A. Mg2 plus Si4 minus and S2 minus. We're going to look at it this way. We're going to have least on the left, greatest to the right. Again, we're talking about atomic radii, how big it is. We need to put these into our answer here. Mg, Si, Mg, Si, S. Mg right over here, Si right over here, S2 minus right over here. Least, greatest. Remember the trend. It increases in size downwards and towards the left. If that's the case, where is the element that is on the very right side? It is obviously sulfur. Sulfur is going to be the least. Then as it gets bigger, it goes towards the left, then I have silicon. And then at the very left, we have magnesium. So, what do you think? Do you think we did it okay? Based on our order. Sulfur being the smallest, and then silicon being the next biggest, and then magnesium being the biggest out of all of them. What do you think? It's actually not the case. Let me explain why. Magnesium is a cation. Magnesium, as a cation over here, is going to lose 2 electrons. Lose 2 electrons. If it loses 2 electrons, there is not much electrostatic repulsion. It's going to be quite compact. If it's going to be quite compact, it's going to be at the very left side. So Mg would actually be here. It'd be extremely small. Then we have to look at our anions, our silicon and the sulfur. This is where we can follow the trend. The silicon has a greater charge than sulfur, so silicon would have to be at the very end here. And then after that, sulfur is going to be in the middle because it has a smaller charge. Remember, the greater the charge, it means it's going to be gaining more electrons. Gain of electrons results in more electrostatic repulsion, hence why silicon is going to be on the very far right side. This is very important here. I'm going to put a star here. The electron that is gained greatly outweighs most aspects. What do I mean by that? Every time you get an electron, which is what anions do, the receiving of that electron creates a very, very strong electrostatic repulsion. So I understand that the magnesium here, it's losing electrons. If it's losing electrons, this means there is not going to be much electrostatic repulsion. However, we need to understand that every time an electron is gained, the amount of repulsion is very, very great. Hence why 4 electrons gained here outweighs the amount of electrons gained here, which is just a 2 minus. And even though this magnesium here loses 2 electrons, it's still not going to be as strong. So what we have here, we have Mg 2 plus, then we have S2 minus, and then we have Si4 minus. Now, all of these, Mg2 plus, Ca2 plus, Ba2 plus, let's have a look at that. How would that look? Mg, and then Ca, and then Ba. We can just follow the trend. Mg would be up here, Ca would be after that, and Ba would be the largest, just by following the trend going downwards in the group. So if we want to analyze that, we have Mg, then Ca, and then Ba. All right, let's do C and D together as well. We have F minus, Cl minus, and Br minus. Least to greatest. Let's look at on our periodic table. F, Cl, and then Br. Where is F? Right over here. Cl over here. Br over here. Quite obvious that the F is going to be the smallest. It's towards the top right. Then the Cl. Then the Br. So far, quite easy. Now let's do the D. Ba 2 plus, Cu 2 plus, Zn 2 plus. Let's order this up. Ba, Cu, Zn. Ba, Cu, Zn. Ba, very, very far left towards the bottom of the group. Then we have copper over here in the middle. And then we have Zn. It's quite obvious that the barium is going to be the greatest in terms of the trend. This is where it gets a little bit of an exception outlier. The copper and the zinc, they're in the same period. So copper is going to be in the middle. And the smallest is going to be Zn2 plus. Barium over here has 135 in terms of its ionic radius. Copper here, this may surprise you, has a 73. Zn has a 74. As you can see, it's a very minuscule difference. However, they should be rearranged. The Cu2 plus should come before the Zn2 plus because the Cu has a smaller number in terms of its atomic size. We have not gone over the Pauli exclusion principle as well as the off-bar rule, so this is kind of out of the scope for this video. For now, think of this as a negligible amount of change. You don't have a data table with you, and you likely will not be given one on an assessment. If you're not given one and these values are not shown to you, follow the trend. So we're not going to actually change this question. The response is going to stay the same. The Zn is going to come first, then the Cu, then the Ba. Just know that during rigorous data testing, it's been exemplified that the Cu should come first. You will not be given this chart, most likely, so I want you to keep it this way. This is a correct response for the scope of the course that you're in currently. So Zn, then Cu, then Ba. Zn, Cu, then Ba. So this is C and this is D. Now let's do the last one, E. We have Si4 minus, P3 minus, and O2 minus. Let's put a scale here, least to greatest. If we look at our chart, periodic table, we have Si4 minus up here, phosphorus 3 minus, and oxygen 2 minus. Based on the trend, our Si4 minus should be quite great. Why? These are exemplified here. Silicon has the greatest amount of charge. The more electrons gained increases electrostatic repulsion, wanting to go towards expansion. So the Si would be greatest in terms of its size. Now we have phosphorus, charge of 3 minus. It gained 3 electrons, which is more electrons than is gained than the oxygen. So the oxygen would be the smallest. This kind of question looks quite simple. However, silicon is a metalloid. Metalloids exemplifies both characteristics of a metal and a non-metal. Silicon, because it's more on the right side of this staircase, should exemplify more non-metal characteristics. Hence why a 4- is written here. However, the way it behaves in nature is not as so. In most textbooks, especially in the new modern textbooks, 4- is never really a question that is asked. The SI is actually a 4+. So if I were to change this into a 4+, our response drastically changes. Let's say we have a 4+, and this is what you're going to be running into. You're not going to be running into an SI 4-. SI 4+, again, it's over here. It's lost electrons. It loses 4 electrons. This means there is going to be extreme effective nuclear charge. So for now, as a safe haven, let's put Si 4+ here on the very left side, because we assume it's going to be extremely small. Remember, it's lost 4 electrons. There is not much electrostatic repulsion. It is going to be extremely compact towards the center of the nucleus. Now we got to start doing our phosphorus and our oxygens. This is where it gets a little bit complicated. Our phosphorus here has gained 3 electrons. More electrons gained means that it's going to expand. So should we put the P3- up here? I would say so. That's quite safe. The difference now becomes the oxygen. The oxygen, it's quite small. But is it smaller than silicon? Remember, silicon is not an anion right now. We changed it into a cation because this is what you're going to be running into. The oxygen, is it smaller than the silicon? Again, if you are not given a data table, you won't know. So there is a very steadfast rule that I want you to understand and to always use it in principle. Si, lost 4 electrons, going to be small. Oxygen, also very small because it's on the top right corner of the periodic table. So which one is going to be smaller? The way we did it is correct. Si is actually going to be smaller. Why? I'm going to put a star here. An electron is very repulsive. Even just 1 electron can do a lot of expansion with its neighboring electrons. Remember, the negatives repel. So even though oxygen is up here and its trend is onto the top right, and you're wondering and you're probably thinking that it should be smaller, it's not the case. Because it is an anion, it gained an electron. Okay, every time you gain an electron, that vastly outweighs how small this cation is. Okay, so because this oxygen is an anion, by nature it's going to be quite great. In fact, if we were to draw a line over here, whenever we cross from a group 14 all the way to a group 15, the change is drastic. From a cation perspective, jumping into an anion category, this nitrogen, for example, is usually twice as great in size than is the lithium. The lithium here is a group 1 element. It is going to lose an electron, right? The lithium here is a +1. If it loses an electron, it's going to have less electrostatic repulsion. It's going to be smaller. All right? Beryllium loses 2 electrons. It's going to be even smaller than the lithium. But even though lithium is not going to be as small as beryllium, the group 15 elements is double the size of a group 1 element. So this nitrogen is double the size of the lithium. And this holds true as you go down. Same thing with phosphorus. This phosphorus can be double the size of this sodium. In fact, there's some data that I can give you here. The sodium here, size of 102. The phosphorus has a size of 212. The nitrogen here has a size of 146. And the lithium, 76. It's a ginormous difference. The point, the moral of the story is every time you have an electron that is gained, the amount of electrostatic repulsion is so great that it is safe to say and it is safe to assume that it's going to be larger than a cation, as small as the silicon 4+. So Si, O, and then P. Okay, if we use an Si that has a positive charge of 4, this is going to be the order. If we use Si 4-, then it's just going to follow the trend of the periodic table that you've been learning as such. So this follows the trend. Follows trend. Down and to the left. This one here doesn't follow the trend.